battling the atmosphere. So one way is to go to redder wavelengths, but that's not always an option in terms of the science you're trying to do. Another way is to get above the atmosphere. That's, as we talked about before, that's why we build telescopes on tops of mountains. Here's Mauna Kea again at 14,000 feet. You're getting above like 30% of the atmosphere. There's 30% less oxygen there. It can make you dizzy. Sometimes people pass out working up there. But the idea is you get above as much atmosphere as you can, but we can't put them on top of Mount Everest because that's far too expensive to operate at that kind of elevation. So there's a limit there. You can, of course, go to space, and that's what the Hubble Space Telescope's about. A lot of people think Hubble is the biggest telescope ever. It's not. Hubble is only 2.5 meters. The Keck telescopes, I'll draw it to scale here, Keck 1 or Keck 2, and there are a handful of telescopes on the Earth now that are of this scale, 10-meter telescopes, so the diameter is 10 meters. So that's 5 meters, that's the Hale telescope. Here's 2.5. So it's 1/4 the diameter, so 1/16 the collecting area of the Keck telescope. It's not the biggest telescope in the world by a long shot, but it's above the atmosphere. That's the great advantage. Even though its diffraction limit isn't as good as the diffraction limit of the Keck, it can take advantage of the full diffraction limit. We did the calculation for the Hale telescope. That was a 5-meter class telescope. And we came up with 0.025. 2.5 meter would be 0.05. It's still 20 times better than what you get through typical atmospheric seeing. So if you can just go up into space, that's great. You have really, really crisp images. Thing is, it's in tremendous demand. I can't remember the exact rate. I think it's 30 to 1. So every 30 proposals, 29 are rejected, 1 gets accepted. I've been part of some teams that have gotten time on Hubble to do various things. But it's hard. Most of the time, you have to make do with what you have available to you on the ground. Okay. Oh, another thing I should say, that doesn't mean, since the Keck is on the ground, doesn't mean it's useless. Keck still has great advantage in terms of light gathering power. You can bring in a tremendous amount of light. If you're doing spectroscopy, you're not really worried about the crispness of your image. You just need a lot of light so you can divide it into the component colors. You still opt for the 10 meter over Hubble. No question about that. You get 16 times more light in the same amount of time. But if you need to make a really crisp image, you try to go for the Hubble. Okay. Here's a comparison. On the left, a star cluster image from the ground. On the right, a star cluster image with Hubble. From the Hubble image, you can see there are hundreds of stars there. But on the image on the left, they're all kind of blurred together, and you don't really know. So there are advantages, even with the smaller aperture. Okay, but as I said, most of us are stuck with what's on the ground. So what can we do? Well, there are 2 things that we do. We can divide them into 2 categories. You have active and adaptive optics. The adaptive optic is the really cool stuff, where we're going to try to untwinkle the stars. We're going to monitor the atmosphere above the telescope and see how it's distorting the light, and then change the configuration of the mirrors in our telescope on that same time scale, like 1/100th of a second. We try to keep up with the atmospheric changes and correct the light as it's coming in real time. Space-age stuff. But before we can talk about adaptive optics, we have to talk about active optics. Active optics, these really don't have anything to do with the atmosphere. These are considerations of good design. We got sloppy. So good design considerations. Being used to, well, it's going to be an arc second of blurring no matter what we do, we got sloppy with the design of our enclosures, with our telescopes, such that once we eventually did have adaptive optics, it was no good, because sloppiness in our design was preventing us from taking advantage of the adaptive optics. Even if the atmosphere were perfect, we're screwing up the light once it gets down to our telescope in 3 different ways. Now big telescopes are designed to take care of these 3 areas of design sloppiness. So let's go through one at a time. The first is dome airflow design. Most telescopes are in traditional domes where they have this little slit that opens to let the light in. But that's about it. The air, it's an opening to the outside. Some air comes in, some air goes out. But for the most part, the air in the dome is trapped. It's stagnant. And that's the worst thing that can happen to your image. If you have stagnant air, excuse me, my cold. If you have stagnant air, it breaks up into pockets, into cells. So we talked about all the cells up in the atmosphere. Don't have atmospheric pockets in your dome. So there are two different types of seeing that astronomers talk about. You have your atmospheric seeing, which is what the sky's giving you, but you also have the issue of dome seeing. And the worst thing possible is to have stagnant air in your dome. It breaks it into pockets. Then even if the atmosphere is being generous to you, your dome seeing can be really bad and can mess up your image. So nowadays they build the domes such that they fold up maximally. And so when you're in full operation, there's barely any dome there. Here's an example. This is the Gemini telescope. It's one of the two Gemini telescopes. There's one on Mauna Kea and one down in Chile close to my prompt telescopes. And you can see it not only has the slit open, but it has its skirt up. That's what we call it, the skirt. And so at the beginning of the night, it raises its skirt and lets the air in underneath. And so you get airflow across the mirror of the telescope. And as long as you keep moving that air, it's less likely to divide into pockets, and less likely to get dome seeing. So that's one example. You need some structure. In case a storm comes by, you can enclose the telescope. If it's a smaller telescope, like the prompt telescopes, those of you in the lab are using these, the domes are a clamshell design. They don't have a slit that opens, they just fold up. Here they are in their open configuration. Ours are made by Astrohaven, a company that charges us a great amount to make them, but they're okay. And they open up and there's no dome. Once they open up, it's like there's no dome and the air just moves through freely. We also have other things to help us move the air around. We have fans. So these are exhausts for fans. We can evacuate of the enclosed air within one of these structures within 3 minutes. We can move that much air. So again, we can encourage the air to move, have good seeing. Even on the mirror, we have little fans that can blow the air across the mirror if we want. If we turn on our fans below and our fans on the mirror, our images improve a little bit. So dome airflow design is very important. Any questions about that? Okay. The second category is mirror temperature control. So the perfect shape for a mirror, as we all know, is parabolic. But now, suppose we make it perfectly parabolic, we put in the telescope, but let's say it gets hot over this region. And maybe just a little bit cooler, so it's cold over here. Maybe we're just talking about a 1/10 of a degree difference. Maybe it's hot over here. Well, glass, there's nothing special about glass. It expands, contracts, or even the glass composites that we use, expands and contracts just like any other substance would with temperature. So the hot region will expand. And not so much, you don't see it with the naked eye. These are microscopic changes. But remember, the light that's coming in here is hundreds of nanometers. And so if you're distorting the mirror on the scale of hundreds of nanometers, even tens of nanometers, the light won't bounce correctly. It'll bounce into the wrong area, and you won't have good focus. These mirrors are really quite amazing. Some of them are 10 meters across. You have to keep that surface perfectly parabolic to the scale of your wavelength. So hundreds of nanometers, actually less than the scale of your wavelength, typically 1/10 of the wavelength. So tens of nanometers, this thing has to be. And if you're heating and cooling, just naturally, how it's touching different things, it can get a little bit hotter, a little bit cooler. That will expand, contract, and ruin your parabolic shape on the scale of tens of nanometers. So modern telescopes are now built with heat sinks on the backs, all over the back of the mirror. What these do, it lets you get rid of extra energy or put energy in to keep the temperature perfectly uniform across the mirror. So you make it perfectly parabolic, and then through keeping the temperature precisely uniform, it doesn't matter if it's hot or cold, it just has to be the same. The whole thing can expand, the whole thing can contract, but if you have patchy expansion and contraction, you lose your parabolic shape. You experience this when you drive over a bridge. You drive in, and as you get on the bridge, you hear the boom, And as you get off the bridge, it's boom, boom again. They have a little divider in the bridge. Concrete, just like glass, expands and contracts with temperature. Most of the road is sitting on ground. And the ground keeps the road at pretty much the same temperature. Sometimes hotter, sometimes cooler. But you can think of the ground as a heat sink, keeping the temperature of the road from changing dramatically. But you go over a bridge, the bridge is just hanging there. It's not touching the ground. It's out in the air. And the air can get really cold or really hot. Hotter than the ground typically gets and cooler than the ground typically gets. So bridges expand and contract the most. And if you build a bridge, say you build it in winter and you don't put those gaps in, come summer it's going to want to expand because it's going to be very hot. And then you get all sorts of cracks and crumbles. And that's expensive maintaining the bridges. So they build these little gaps in. And so in summer, the gaps close. And in winter, when everything contracts, the gaps widen, but not so much that your tire is going to fall through. So it's in winter in particular that you hear the boom as you go across. So just an everyday example of this. And then the final thing that you have to worry about is mirror shape control. And specifically, I'm talking about the shape of the primary, the large primary mirror. You'll see when we talk about adaptive optics, we'll have a little mirror that's moving and changing its shape really quickly. Here with active optics, we're just talking about the large primary mirror. And this comes from taking that mirror, it's perfectly parabolic when looking up, and then turning it sideways. You know, it's designed to be perfectly parabolic when gravity is pulling on it this way, but you tilt it in a different way, gravity will pull on that in a different way, and that's going to change the shape of the mirror by more than tens of nanometers. Still not enough that you might see it, but it does change it. And so now, what we do is we don't build thick mirrors, we build them kind of thin. And I think, if I recall, this is a picture of the SOAR telescope's mirror. SOAR's UNC signature telescope, 4-meter mirror. And so, instead of just sticking it on a basic support structure, we stick it on a whole bunch of pistons. So here, underneath the SOAR telescope, you have, I believe, 128 pistons. You start by putting the mirror on it. And again, the mirror is made very thin. With the SOAR telescope, it's a 4-meter mirror, but its thickness is only 4 inches. Makes you a little worried when you transport. The mirror is made in Connecticut. We have to get all the way to Chile without breaking. And it's so big, yet so thin compared to its extent. But still, the idea is, if it's thin, you can bend it pretty easily. You stick it on these pistons, and you adjust all the pistons such that it's perfectly parabolic. And you know it's perfectly parabolic when your stars are in focus. Then you tip the telescope over and look at a star at a different angle. And you have to figure out how to adjust all the pistons such that that's in focus. Then you do a different position, and a different position, and a different position. It takes a whole year, really, to figure out how to control all these pistons to keep your mirror in its perfect shape no matter what position. But once you figure it out, it's all stored in the computer. Whatever position you go to, you load in the configurations for all the pistons, and it pushes your mirror back into the perfectly parabolic shape. Kind of morphs it. That's pretty cool technology, and that's in place on all modern telescopes. They're built this way now. So the 3 things to active optics are the dome airflow design, the mirror temperature control, the mirror shape control, but here's the difference it makes. So this is an image from the New Technology Telescope where these 3 things were really explored back in the 90s. European telescope in Chile. It's actually an infrared image. So it was a really good night. Here we see 5 arcsecond scale. So this is 1 arcsecond. You see the stars are much smaller than an arcsecond across. So it's 0.1, 0.2, 0.3 arcseconds seen. So the atmosphere on this particular night is really good. But on the left, we lower the skirt of the dome. We turn off the mirror temperature control. We turn off the piston control. And you see how blurry the image gets. So before you can even do battle with the atmosphere, you have to have these things in place. Questions about active optics? Okay? So that's kind of boring stuff, but once you have it in place, you can do the cool stuff, and that's the adaptive optics. Adaptive optics is kind of really cool space-age technology. First developed by the military. They're looking through the atmosphere too. They're not looking up, they're looking down. It's
spy satellites developed this technology. If they want to read a license plate from orbit, that light's being refracted as it's coming back up too. So they developed these kinds of techniques. They didn't share their findings with us, so we had to reinvent the wheel on this, the astronomers, but they're probably still much better than we are at doing it. But we've gotten pretty good at it.
And so the idea with adaptive optics is if you want to look at something faint, like a galaxy, you might have to have your shutter open for a whole hour just to get enough light to see the way you want. Spirals are supposed to all go the same way, but I screwed it up. But there's our galaxy. If you have a bright star nearby, and you put video just on this bright star, you don't have to have video on the whole image, because in 1/100th of a second you won't see any bit of the galaxy. But you have video just on the bright star, you can watch how the atmosphere is pushing it around. If you have really fast computers, you could adapt to it and push the star back to the same spot on your image. I have a video here, but for some reason it's not loading. It loads fine on my computer, though when I push it up it doesn't. Let me just try one more time. Maybe I can open it with something else. I'll open it 2 ways and see if either of them work. So I see it on my screen. If I bring it over here, okay, so I'm just going to have to explain it without the video and debug that later. Okay, so that was a video of the Gemini telescope, and I'll just kind of explain it here. And we're doing good with time. So here's the Gemini telescope, and light's coming in, bounces off the primary, bounces off the secondary, goes through Cassegrain into the adaptive optics module on the back. And we'll zoom in here and see what we see. So if we look in this box, the light's coming down, and it bounces off a sequence of mirrors. But this mirror is kind of a special mirror. Oh, thank you. This mirror is a special mirror. And this mirror is a special mirror. Okay. So down here we have the camera. So light's coming in, bouncing into the camera, and the camera feeds to a monitor. And this is a video camera. You're just looking at this bright star. And you're seeing it moving all over the place. And it's not just moving, it's distorting too. Sometimes it's getting small and big. So it's being pushed and pulled around the image by the atmospheric changes, but also stretched and contorted. You can think of it, if you think of the light fronts, coming down distorted, bouncing off the mirror, coming in distorted. And what happens, this is called a half mirror. It lets half of the light through, and half of it bounces. Over here you can have another camera. This can actually be your video camera. And if you have a fast computer attached to it, it can read where the star is very quickly and send commands back up to this. This camera can be, this mirror can be tip-tilt, and or it can be deformable. Many telescopes use tip-tilt. That's the simplest thing. So suppose the star is drifting over to the left. With this mirror, I can change its angle, pushing the star back to the right. So as the star starts to wander this way, I change this in the same time, 1/100th of a second, keep it here. I'm always lagging behind the atmosphere a little bit, but we can stay pretty much on top of it. The closer we are to being on top of it, the better this effect is. If it starts moving over this way, we can push it back. Always keep the star there. If we can always keep the star there, this galaxy will always stay there as well. And I can keep the shutter open for a full hour and get a nice crisp image. So if I finish this example, this mirror is tipping and tilting very fast, like 1/100th of a second. And you don't see it. It's not big angles, very, very small angles. To the human eye, you don't see any change. But you hear it. It's humming. It goes zzz, because it's going, like this, really fast. Small angle deflections. And it hums. And what it's doing is it's pushing the star back. Gemini ones actually have a deformable mirror. So it not only tips and tilts, but it morphs. I know, that's weird looking. But you get the idea, and it straightens out these light fronts. So by the time the light gets down here, it stays in a point. Tip-tilt keeps it from moving, and the deformable part keeps it from spreading out. So if you can keep that in place, anything within this star's atmospheric cell, suppose the atmospheric cell is this big, anything within this star's atmospheric cell will stay in place. So it's a pretty cool system.
Here's the movie. Okay. We'll just go and fast forward here. Here's light going down into the system. Going to take a look into the adaptive optics unit. Coming down in. Here's light. It's going to bounce off that mirror, half mirror, then out over to the computer. There you can see the atmosphere deforming it. And if we look closely, here come the wave fronts, all deformed by the different atmospheric pockets. And let me just stop it here. We're dividing the light into two parts. Some of it's going to the camera, but a little bit's coming through. You can build a system that's a half mirror. It comes through and it's detected here. And what this does, it's really hooked up to a computer. It's measuring how the stars are being deformed and how they're being pushed around across the image. And then that computer, very fast, kind of like a supercomputer, is sending commands to pistons under a flexible mirror and makes the mirror flex in just the right way to straighten out the light fronts so we don't get the atmospheric distortions. We still get it to some degree. There's no way to get rid of it completely.
So here's an example. Here's Neptune. This is taken by the Keck telescope. All the active optics are in place, but the adaptive optics are turned off at the moment. Now, those of you in the lab, many of you image Neptune. With our telescopes, it's just a blur, but it's a bigger blur than the stars around it. It was an extended object. Here, Keck can do a little bit better with its active optics. You can see there are some features on it, maybe a cloud or a storm, it's hard to say. But then you turn on the adaptive optics, where you're battling the atmosphere, untwinkling the stars, and this is what you see. So it's too expensive for us to put a 10 meter in orbit, but we can cancel out a greater portion of the atmospheric distortion with these systems. It's almost like we're imaging from space. Not quite, but we can approach that limit. And so you can see there are bands of clouds and a storm and pretty cool stuff. And still cutting edge technology, but it's becoming more and more standard. And one last thing.
But there's one problem. And that is you don't always have that really bright star close to what you're looking at. Now, the nearest bright star might be all the way over here. And that's too far away, because as we're looking up through the atmosphere, as we said, there are different pockets. This might be one atmospheric pocket. This would be another. If your bright star is really far away, what the atmosphere is doing over here has nothing to do with what the atmosphere is doing here. This might be moving this way when this is moving that way. So you can't use this to correct that if it's far away. We call this a guide star. It's our guide. The closer the guide star is, the better you can do it. And given the current limits of the technology, there aren't sufficiently bright stars next to every point in the sky. It's only about like 10% of the sky. So most of the time we have to make our own. When you go to modern observatories at night, and it won't be perfectly dark, you'll see lasers coming out of the big telescopes. And these are called artificial guide stars. And so we have two types. We have natural and we have artificial. We can take a high-powered laser. I mean, these things are powerful. Don't stick your hand in front of it. Burn a hole through your hand kind of laser. And we shoot it up into the sky, and it bounces off the atmospheric particles and comes back, and the light gets in our image. Since it's starting on the main axis of the telescope, laser's right up at the top of the telescope, it comes back as an artificial star. Most of that light goes into space, but some of it bounces off the atmosphere and comes back. And it gets distorted on its way back. And so, in some ways, these are even more useful. It's not going through the whole atmosphere, but bouncing off at all sorts of different heights. And we can get different height information about what the atmosphere is doing, model it better. So sometimes these are better than natural guide stars. So that's kind of nifty. You go to question. Let's move in. This is a time-lapse photo. And so you're seeing the stars trail across the sky. It really is quite dark here, and so you don't notice it in just a quick snapshot. They leave the exposure on for a long time so you have enough light to see the telescopes. The sky's rotated. It's probably like a 15-minute exposure. Yes?
Last time you said there was
Yeah. If we're talking about the primary, the big mirror in the bottom, so when you move the telescope and you adjust its shape once after every move, that's active. But this little itty-bitty adaptive, this little itty-bitty flexible mirror, tip-tilt mirror that's buzzing because it's moving so quick, connected to the supercomputer, that's adaptive. You don't do that with the primary or the secondary. It's usually a very small mirror somewhere along the optical train. Okay, so that's active and adaptive optics. Any questions about that?